All right, so 10-2 is all about regression. And before we go into regression, let's just summarize what this whole chapter is really about. The whole chapter is trying to figure out, is there a relationship between two variables? And so the steps that we take to determine this is, first we collect our data, which, because we're doing this, all of our data is given to us. The next thing we do is we create a scatter plot. From the scatter plot, we can see what type of nature it has, such as, is it positively linear, or is it negatively linear? Is there no relationship? Is it curvilinear, or does it follow like a exponential or quadratic sort of shape? Then after we do that, we can determine the correlation coefficient, which is determined by the variable r. And I created that Excel spreadsheet for you guys so you can easily determine what is the correlation coefficient very, very quickly. After that, we test the significance by our hypothesis testing. When we do this, we can either reject or keep our claim, and which is always to figure out, is there a significant difference between the correlation coefficient and r. And after we test the significance, if it is significant, that is when we are allowed to go to the next step, which is to find the regression line. So the regression line is the data's line of best fit. It's not the exact line that the data points follow, because obviously it's a scatter plot, so there is not really a single line or a linear function that can encompass all of that, but we can get really close. And so we never find this regression line if r is not significant. So don't waste your time. If you end up doing this hypothesis testing and you determine that there is insufficient evidence to say that there's significance, then you wouldn't have to do this next step, because it would be a moot point at that time. So the purpose of the regression line is to make predictions, okay? And it's important to understand that these predictions that we're making are not so very far in the future or so very far in our data, but more so that we can make predictions within our data, and I'll explain that in a second. So some things to know is the residual, and the residual is the difference between the actual value of y and the predicted value of y. So if we go back here, our residual is going to be the distance between our actual point and our predicted point. And so as you can see, our line of best fit is sort of in between, where our residuals could be above it, or distance above it, or distance below it. I will say that sometimes our line of best fit, there's a lot of different possibilities. If you look at the book, it sort of goes into a bunch of different possibilities, which I didn't, but that's not super important. What you do need to know is that the residual, it is just the difference between the actual and the predicted value, or the vertical distance. It is used to find the line of best fit. Sometimes it's called the method of least squares. And so because it's sometimes called the method of least squares, finding the regression line is sometimes called the least squares regression line. And I'm just throwing that out there in case you go into maybe a level 4000 statistics class in college, which I had to do, and sometimes terminology changes. So I'm just telling you some extra information just for your general benefit. So how do we find the regression line? Well, we have to use this formula. So there's a lot of different methods, but for the sake of this book, we're going to be using sort of a spin-off off of the linear function from Algebra 1, which is y equals mx plus b. So we can sort of see the general idea of y equals mx plus b right here, except because we don't have a perfectly straight line, we have to modify it a little bit. So instead of it being y, which is the actual, we have y with that little tick mark, and that is just saying that the predicted y is now going to be equal to a plus bx, a plus bx, where a follows this formula and b follows that formula. And it's important to know that a represents our y-intercept. It represents our y intercept, and our b is now going to represent our slope. With this, you should always round to 3 decimals, so it's very similar to the residual plot in that manner. And so let's do a quick example. All right, so steps to finding the regression line, we can use our previous example where we had the car rental companies and the number of cars that they had, or the average of the cars that they had, and the revenue that they obtained. So this is actually one that we've done before, and I'm not going to make us go through all the steps again. I just went ahead and put all the information into our table here. But the first thing we would have to do is to create this table depending on what we have. And again, all of this is going to be a lot easier for you guys because I created that Excel spreadsheet for you. But after we find all of our pieces, we can go ahead and start following our formula, which is step 2. When R is significant, which we've already determined it is based on the previous video, we can now use our formula for A. So let's plug that in. We got A equals, and then sum of y is going to be 18.7, sum of x squared is going to be that 5,000, all right, minus the sum of x, which is 153.8, times the sum of x times y, which is 682.77. All right, all of that is going to be over the n, which on the Excel spreadsheet I did not put n because it looked silly. I put count. It's just the count of everything. So 6 times the, let's see, x squared would be the 5,000 number again. Oops, okay, all right, fixed it. And then we subtract our x, the sum of x squared, which would be 153.8 squared. All right, so we use our calculator, we type all this in, and we should get approximately 0.396. Approximately 0.396. And then we do the same thing with our B formula. So B is going to equal 6 times, x times y is going to be that 682.77, minus the sum of x times the sum of y, which is 153.8 times 18.7. All of that's going to be over 6 times that 5,000 number minus 153.8. Let's put this parentheses squared. All right, type that into our calculator. Should be very straightforward for this part, but we don't have the square root in any of these formulas, which is very nice, but we should get approximately 0.106. I'm just rounding to 3 decimals each time because I want to keep it similar to my residual, not my residual, my correlation coefficient. All right, so now that I have all my pieces, I can plug it into my formula. It's going to be the predicted y is equal to 0.396 plus 0.106 times x, and this is my answer. All right, so that is the process that you have to take in order to find your regression line. All right, let's do one more example just so that we have this solidified. The instructions here say use the equation of the regression line to predict the grade for a student who has missed 4 classes. And we've actually, again, we've done this before, but I'm actually going to use my Excel spreadsheet to sort of help me plug in all my pieces. So let's go to the Excel spreadsheet. All right, so here's my Excel spreadsheet. I went ahead and typed in everything. And I have a correlation coefficient, or an R, of negative 0.944, which I can look at that. I can see that's really, really close to -1, so I can just look at this and automatically know it's going to be significant, even if I, hadn't already done this problem, which we already did. We did this one yesterday, or we did this one on the previous video. So I'm going to take all of my sums that I have off to the left-hand side, all of these pieces, and I'm just going to write them in my on my PowerPoint. All right, so I'm going to copy all this over. I'm going to write n equals 7 just so that I remember that. Copy my numbers down, which is 57, 511, 3,000-ish, 579, and then 38,000. Then I'm going to go ahead and write down my formulas that I'm going to need because I've already determined it's going to be a significant relationship. So I'm copying down my formula for A, trying to keep the colors consistent, and I'm going to plug in my numbers. So I got 511, 579 minus 57 times 3,745, all that over 7 times 579 minus 57 squared. And if you plug that into the calculator, it should be approximately 102.493. So part of the reason I wanted to do this example was so that you guys can see that when we're doing this, sometimes we're going to end up with small numbers, but sometimes we're going to end up with big numbers. And I don't want you to think that you're doing it incorrectly just because you end up with a larger number, larger than 1 or whatever. This isn't our correlation coefficient, which is limited to -1 to +1. So if we get beyond that, that's okay. So then letter B, writing our formula, n times the sum of xy minus the sum of x times the sum of y, all of that over n times the sum of x squared minus the sum of x quantity squared. Plug in all of our pieces with 7, 3,745 minus 557 times 511 over 7 times 579 minus 57 squared. All right, so I'm going to type this in my calculator really fast so we can get our answer, and we should get a negative 3.622. All right, so I have all my pieces, and now I'm going to plug it into my equation of my for my regression line. So predicted y is going to equal 102.493 minus 362 or 3.622 x. And so that's my answer. Well, not really. It's the beginning of my answer. I have my regression line, and now I have to use it to predict what is the grade for a student who has missed 4 classes. So I'm just going to plug in 4 as my x, because remember, x is the number of absences. That's what we're controlling. That's our independent variable, if you will. So I'm going to rewrite all of this and plug in my 4. All right, so now that I plugged that in, take a calculator, type in the whole thing, and you should get 88.005. And if we round it, it'll just be 88%. And so this is my final answer. So the whole purpose of this is to predict, well, what would your grade be if you missed 4 days? So it's important to understand 2 things. The first thing is that we're making a prediction within our data points. We're not making a prediction beyond it, and I'll explain that in 1 second. But the second important thing that you should probably note from this is that your correlation coefficient, the sign of that, which our correlation coefficient for this problem was a negative 0.9, etc. I think it was 944. But it was negative. So the sign of your correlation coefficient should always match your slope. And remember, B is your represented slope in statistics, not algebra 2. Algebra 2 is different. But for this one, it's important to know that your correlation coefficient and your slope are going to be the same sign. And part of the reason why you should know this is because you can use that knowledge right there to understand if you make a mistake. If you are doing the work and let's say you mix up some of your formulas or some of your summations in your formula and you end up with a negative correlation coefficient but a positive slope, well, you've made a mistake somewhere, probably somewhere in your formula, because my Excel spreadsheet is infallible. Ha ha ha. No, it's not. But that's not the point. So having these general pieces of information is really helpful in determining if you've made a mistake and also where you've made a mistake. All right. So the final piece is going to talk about that previous thing that I said before, which is that we're making predictions within our data points. So it's important to know that extrapolation is the term that we would use for making a prediction beyond the bounds of data. All right, so within our information. So when we were looking at our absences and our grades and stuff, that term that we would sort of use for predicting within our data, we would call that a point prediction. Okay, that point prediction is within our points, if you want to think about it as that. But beyond our data, we would call that extrapolation. Okay, so that is beyond any of our points. What would it be in the future? Things like that. You have to be really careful when you're making predictions beyond your data points, because it is on the assumption, it's on two possible assumptions. One of the assumptions being it's based on your present condition. Well, the problem is that our present condition is not always constant. It changes from day to day, even from hour to hour. The other thing is that the other assumption we have is that this trend will continue. So, for example, back in the early 80s, there were statisticians who were saying, for America at least, that we would run out of oil by the year 2003 or something. And they ended up being wrong because, they were assuming that our trend of oil consumption would be constant or consistent. But it ended up that after that, companies started to find, fuel efficient vehicles. They found other oil locations with larger sort of amounts of oil. And so because of that, both of those sort of assumptions sort of crumbled. The present information or the present condition changed, and also the trend changed. Okay, so extrapolation can be useful. It can be, but it can also be inaccurate. The other thing you need to know, and it's not really related to extrapolation, it's just in general, is that you should always, when you're doing stuff like this, check for outliers. Because remember, our correlation coefficient and all of our points really are very sensitive to outliers, and it will affect our regression line in one way or another. Typically, it causes the regression line to pull towards that outlier, and so what statisticians typically do, and we're not going to do it, but just for general information, statisticians will typically draw the scatter plot with the regression line with the outlier, and then they'll redo it again without the outlier, and then recalculate everything without that outlier or supposed or alleged outlier. And if they see that the regression line did not really move much, well, then they know it's not an outlier. But if it is moving significantly, then they would say, okay, this is definitely an outlier. And so because of this, they call these very influential points or influential observations. And so just general information for you guys. That is not something we're going to be doing in this class because it is a high school statistics class. So with that bit of information, I hope you guys enjoyed this video. Hopefully it wasn't too difficult. Make sure you do your homework. And again, if you have any questions, please make sure that you reach out to me.